Is part 2 of the integration techniques. So now we're looking at some definite integrals with u substitution or u substitution techniques. Okay, so the first example, I see the x squared plus 1 in the denominator, the x is in the numerator, so that makes my life easier. That tells me it's a good candidate for u substitution. One thing we must keep in mind whenever we are doing u substitution, we must change our bounds to the u as well from x. So don't keep your bounds in terms of x, change your bounds to the u substitution, u bounds. Okay, so the example number 7 I'm going to let x squared plus 1 be the u, 2x dx be du, x dx be 1/2 du. Okay, so also I can see when x is 0, u would be equal to 1, and when x is 4, u would be equal to 17. So on the top I have 1/2 du, on the bottom I have u, and that's going to turn out to be 1/2 natural log of u. Bounds are from 1 to 17. If we change the bound from 1 to 17, we can go ahead and plug them in now. No need to add the constant c because it is definite integral. It is not indefinite integral. Natural log of 17 minus natural log of 1. What is natural log of 1 equal to? Natural log of 1 is 0. So it would just be gone. 1/2 natural log of 17 is what I'm going to be left with. Okay. Next example. I can let, in this one, I can let cosine x, I can let the sine x be u, let the sine x be u, cos x dx would be du. So this entire thing would be du, sine x is u, so I have u to the 4th du. When x is 0, sine of 0 is 0. When x is pi over 2, sine of pi over 2 is 1. So this becomes u to the 5th over 5. The bounds are from 0 to 1. So we can say 1 to the 5th power, which is still 1, divided by 5, minus 0 to the 5th power. 0 divided by something is just 0. So my final answer is 1/5 here. Next example again, we can let sine x be the u, and then cos x dx will be our du. Okay, so this becomes 4 to the power u du. When x is 0, u will be 0. When x is pi over 2, u will be 1. What's the integral of 4 to the power x or 4 to the power u? It is 4 to the power u divided by natural log of 4, going from 0 to 1. Okay, so 4 to the power 1 over natural log of 4 minus 4 to the power 0 is 1 over natural log of 4. And that would be our answer. Actually, we can simplify it to 3 over natural log of 4. All right. Manipulate the next equation. Cos squared theta is 1 minus cosine 2 theta divided by 2. And sine squared theta is 1 minus cosine 2 theta divided by 2. Recall this. This can be all derived using the double angle formulas. Go ahead and give it a try to derive and also memorize these two. Okay. Now I'm going to evaluate the integral of cosine square x. That I'm going to change it to 1 plus cosine 2x divided by 2 dx. We can integrate the pieces. 1/2 dx, integral is just x over 2, and integral of cosine 2x is sine 2x, but I must divide by 2. Add a c, it is indefinite integral. Okay, there we are. Next one, we have sine square x, the same. I'm going to use a double angle formula here. Sine square x is 1 minus cos 2x dx, isolate into two integrals, cosine 2x over 2 dx. Okay, so that's 1/2 x minus, you already have the 1/2 in, you already have the 2 in the denominator, pull it out. And integral of cosine 2x is sine 2x, but I must divide by 2 as well. So it's 1/2 x minus 1/4 sine 2x plus c. All right, next few examples involving trig as well. Again, we'll have to be creative with these. 1 over 1 minus sine squared theta. How can I integrate 1 over 1 minus sine squared theta? There's nothing in the numerator. So one thing I know, sine squared 1 minus sine squared theta, using Pythagorean identity, it is equal to cosine square theta, which turns out to be secant square theta d theta, because 1 over cosine square is a secant square theta, which turns out to be, is there a function whose derivative is secant square theta? Yes, tangent theta plus c. Okay, next example. This one is a bit tricky. I did try rationalizing. That didn't help me out. So here we have to use a clever technique. Divide top and bottom with a cos square theta. Okay, and that's going to leave me with secant square theta over secant square theta plus tangent square theta d theta. Okay. We recall our basic Pythagorean identities. Sine square theta, sine square x plus cos square x is equal to 1. If we divide everything with the cos square x, then we have tangent square x plus 1 is equal to secant square x. So I do have a way of writing this secant square in terms of tangent square x or tangent square theta. The reason why I'm interested in doing that is because I'm going to let tangent theta be the u. Let tangent theta be u, because I see the derivative of tangent square theta sitting right on the top. Secant square theta d theta be du. Okay, so here we are. We have du on the top. I'm going to write this secant square theta in terms of 1 plus tan square theta. So this is 1 plus tan square theta plus tan square theta, which is du over 1 plus 2u, because then I have 2 tangent square theta, and I am calling the 2u squared. Du over, yes, it would be 1 over 2u squared. All right, so again, let's express it as du over 1 plus root 2u squared. Okay, looks somewhat like tangent to me. We can do another substitution, or if you see the tangent directly in there, go for that. If you don't see the tangent directly in there, then you can let root 2u be the t. Root 2u, this whole thing is, no, u is not in the square root. Okay, hold on. Let root 2u be t. Okay, so root 2 du will be dt. Or we can say du will be 1/2 1 over root 2 dt. Okay, so this integral would turn into 1 over root 2 dt over 1 plus t squared. Which one is a very famous tangent inverse t plus c? 1 over root 2 tangent inverse. What did we call t in the beginning? The t was root 2u plus c. And what did we call u in the beginning? let's see, the u was tangent theta. Because we had the theta in our problem, we need to go back to theta. And this will be the integral for that problem. This will be the integral. Don't forget the constant c. Okay. Next example, we have cos 2x over 1 plus sine 2x squared. In this case, I'm going to let 1 plus sine 2x be the u. If I let 1 plus sine 2x be the u, then I have 2 cosine 2x dx be du. I already have cosine 2x there, so I can say cosine 2x dx be du divided by 2, or half of du. So I have half of du over u squared. Now we can take it to the top, and now we can add 1 to the exponent and divide with the new exponent. That turns out to be 1/2 u to the power negative 1, and I have negative 1 in the denominator, which makes it positive, plus c. Negative 1/2 1 plus sine 2x to the power negative 1 plus c. And that's what our integral will be equal to. Okay, example number 14. Here we have e to the power t divided by e to the power 2t plus 2e to the power t plus 1 dt. Now, denominator definitely looks like a perfect square to me. If you square e to the power t plus 1, you would get that if you FOIL this. So I'm going to let e to the power t plus 1 be the u. E to the power dt would be du. So the entire numerator becomes my du. So this becomes du over u squared, which is u to the power negative 2 du, which is u to the power negative 2 plus 1 over negative 2 plus 1, which is negative u to the power negative 1 plus c. Okay, what did we call u in the beginning here? E to the power t plus 1 to the negative first power plus c. Okay. Again, we can bring it in the denominator because that's what the negative exponent means. All right, next few examples. Okay, again, for u substitution, remember to do the change of variables. If you go for a definite integral, if you're using the u substitution, do not forget to change your bounds as well, from x bounds to u bounds. Okay, so next several examples would be involving that. We're going to let x squared plus 1 be the u here, 2x dx be du, x dx be du divided by 2. Okay, when x is 0, u will be 1. When x is 1, u will be 2. And 1/2 du, u to the third here. Now we have 1/2 here. Integral of u to the third is u to the fourth over 4 from 1 to 2. So 1/2 in the front, 2 to the fourth power divided by 4 minus 1 to the fourth power divided by 1. 2 to the fourth power is 32 over 4 minus 1/4, and that comes out to be 31 over 4, which is 31 divided by 8. Okay, the next example, so as we have talked about area under the curve, so this is the area under this curve. Integration, this is the area between the x-axis and the curve, area under the curve, from 0 to 1. Okay. Next example. Here, I don't have any x sitting outside in the front, so I'm going to let 2x plus 1 be the u, 2 dx will be du, dx is 1/2 of du. Okay, so we have square root of u, half of du. When x is 1, u would be 1. When x is 5, u would be 9. Okay, so we have 1/2. U to the power 1/2 plus 1 is 3 over 2. Also divide by 3 over 2, which is multiplying by 2/3. No need to add a c. It's a definite integration. My bounds are 1 to 9. So we have 1/2 2/3 9 cube square root minus 2/3 1 cube square root. Okay, what is square root of 9? Square root of 9 is 3. 3 to the third power is 27. Minus 2/3 cube root of square root of 1 is 1, and 1 cubed is just 1. Okay, so that's 1/2. We can simplify. That's 18 minus 2/3, and then go ahead and simplify this. I'm going to leave it at this point. All right, here the extra variable we have it's not found in the extra variable is not found in the u. Extra variable is not found in the u that you call. So we have to manipulate a little bit more. Let's go ahead and I'm going to let 2x plus 1 be the u. And from here I can say 2x is equal to u minus 1, x equal to u minus 1 divided by 2. Also, from here I can say 2 dx is equal to du, which means dx is du divided by 2. All right, so 1/2 du x is equal to u minus 1 over 2 square root of 2 du. Okay, so I can pull the 2 out. So there's my 1/4, and I have u minus 1 times square root of u du, which turns out to be 1/4. U times square root of u is 1 plus half, which is u to the power 3 over 2, minus u to the power 1/2 du. Okay, so when we do the integration here, add 1 to the exponent. 3/2 plus 1 is 5/2. And I'm also dividing with 5/2, which is same thing as multiplying by 2/5. And 1/2 plus 1 is 3/2. I'm also going to divide with 3/2, which is same thing as multiplying by 2/3 plus a c. That's my constant of integration. Next example, number 2. We have definite integral in this case, so there's bounds. So I'm going to let x squared plus 3 be the u. 2x dx be du. Okay, so what we're going to do now is, I have x cubed on the top. So what can I do with that x cubed? Let's think about it. So I do need 1x with the dx to go to my u values. I can write it as x squared times x dx over x squared plus 3 times 5, going from 0 to 1. Now that looks like a nicer problem because this entire thing will be my du. So half. And I can also say x squared will be u minus 3. So I have u minus 3 du over u to the 5th power. Let's go ahead and simplify that now, because we can isolate our fractions. Leave the 1/2 in the front. U over u to the 5th minus 3 over u to the 5th du, which is 1/2 u to the negative 4th minus 3 u to the negative 5th du, which is 1/2. Let's go ahead and do the integration now. I actually dropped the bounds, so I should keep the bounds in terms of u now. When x is 0, u is equal to 3. And when x is 1, u is equal to 4. So from 3 to 4 are my bounds. Okay, u to the power negative 4 would be negative 4 plus 1 is negative 3, divided by negative 3, minus 3. U to the power negative 5 plus 1 What's negative 5 plus 1? Negative 5 plus 1 is negative 4. And divide by negative 4, it would actually become a positive here. Add a c. And the bounds are from 3 to 4. Okay. I'll leave the rest for you. Simplification, use a calculator. Plug the 4 in first and then the bound 3 in and subtract the values. Okay. All right. Next problem. Sin x over cos square x dx looks like I can let cosine x be u. That would give me sin x dx be negative du because I would have a negative derivative of cos x is negative sin x. So I have negative du over u squared, which is u to the power negative 2 du, which is negative u to the power negative 2 plus 1, which is negative 1. Divide by negative 1 plus c. The negative and negative will make it a positive, so it's just u to the power negative 1, which is 1 over u plus c. And that's 1 over cos x plus c is what I would be left with. Okay, the next problem, cotangent x times sin x. There's no function whose derivative is cos x times sin x. So what I can do here is I can change the cotangent into cos x over sin x times sin x dx. Okay. Good. Cos x, sin x and sin x can be cancelled. So all I'm left with is the integral of cos x dx. What is the integral of cosine x? Integral of cosine x is sin x plus c. It's an indefinite integral, so we need to have the constant, arbitrary constant c in there. Example number 5, secant square x plus sine x minus cosecant square x dx. We can just go ahead and do the integration of pieces. Here it is tangent x minus cos x cotangent x plus c. Because integral of cosecant square x is negative cotangent x, and that would make it a positive. Integral of cosecant square x is negative. Let me double check. Yes. The negative and negative would become a positive. All right, so next problem, again, I can do the integral of pieces here. We can break it into two separate integrals, and it would turn out to be, once I do the integration, negative secant x, because the integral of secant x tangent x is secant x, and the integral of cos x is sin x plus a c. Okay, let's review integral of bases. Integral of e to the power x is e to the power x, but how about if you have a base other than e, then it's b to the power x natural log of b plus a c. Integral of 1 over x dx is natural log of x plus c. Okay, here's the derivative of inverse trig function formulas, and backwards would be the integration formulas, so make sure you remember all of these. So if you do integral of 1 over square root of 1 minus x squared dx, that would be sine inverse x. So remember all these basic inverse trig, derivative, and integral formulas. I believe I have integral formulas on the next page. There we go. So they're just backwards from there. Okay, let's look at the examples. Here we are, evaluate each integral. So this is going to be, this one looks like tangent inverse x from 0 to 1, which is tangent inverse 1 minus tangent inverse 0. Tangent inverse 1 is pi over 4 minus 0, and pi over 4 is what my answer is going to look like in this case. Okay, the next example, we have, again, I'm going to try to do u substitution here. Looks like it should be sine because x squared is like 1 minus x squared, but I want to make a 1 over here. So pull out a square root of 9 from the square root. Pull out a 9, and that would, okay, dx over square root of 1 minus 4 over 3x squared. I'm pulling out a 9. Maybe I shouldn't skip. I am skipping one step. It might help you to see that step as well. So dx divided by 1 minus 16 over 9x squared. I'm going to write it as a perfect square now. 1 minus 4 over 3x squared. Okay, so I'm going to let 4 over 3x be the u. So 4 over 3 dx be du. And I can say dx will be 3/4 du. So 1/3 in the front, 3/4 coming from du, square root of 1 minus u squared. Okay, what is, let's see. So 1 minus u squared is sine inverse u. So we have 1/4 sine inverse u plus c, which gives 1/4 sine inverse. What was the u here? The u is 4/3 x plus c. All right, so next example. Here we are, number 3. Again, the same kind of technique. I'm going to pull out a square root of 4, which is 1/2 outside, and I would be left with 1 minus 5 over 2x, everything squared. Let 5 over 2x be the u. And that means dx is 2/5 du. So we have 1/2 times 2/5 du divided by 1 minus u squared, which is 1/5, and sine inverse of u plus c, which is 1/5 sine inverse of u is 5 over 2x plus c. Okay, good. So the next example, let's check this one out. We have x in the front and secant. This looks like one of the inverse secant to me. So let's go ahead and evaluate this integral. First step, I'm going to 1 over 2 root 2 to 1/2 dx over x. I'm going to write it as a perfect square. Instead of writing 16x squared, I'm just writing square of the 4x. Okay, so I'm going to let 4x be u, 4 dx be du, dx be 1/4 du. Okay, and I can also say from here, x would be u over 4. All right, so a lot going on in this problem. So first of all, I'm going to replace this x by u over 4. So I have a u over 4. It will go on the top. And then dx, I'm replacing by 1/4 du. So 1/4 du. And then I have square root of u squared minus 1. Let's take care of the bounds now. When x is 1 over 2 root 2, u is 4 times this x. U is 4 times 1 over 2 root 2, which turns out to be 2 over root 2. And when x is 1/2, u is 4 times the 1/2, which is 2. Okay, now it looks a little bit more doable now. So we have secant inverse u, and the bounds are 2 over root 2 to 2. Secant inverse 2 minus, we would plug in the bounds now here. Because, yeah, we did change the bounds to u bounds. So go ahead and evaluate this using the calculator. Okay, just plugging the upper bound and subtracting. So all you have to do is secant inverse 2 minus secant inverse 2 over root 2. Okay, it can be done without a calculator as well if you remember your special acute angle cosine values, then you have the secant values from there as well. Okay, the next example, number 5, we have x over x to the 4th plus 1. If I let x to the 4th plus 1 as u here, then 4x to the 3rd dx be du. 4x to the 3rd dx be du, and we can say x dx, yep, 4x to the 3rd Let's not, this seems like it's not going to work out. Let's not call x to the 4th as u. Let's call x squared as u. 2x dx be du. X dx be 1/2 of du. Okay, so we have half of du divided by u squared plus 1, right? And that looks like this would be a tangent inverse u plus c. Now plug your u back in there. We called u as x squared. So it's 1/2 tangent inverse x squared plus c. Where did it go? Here it is. Okay. All right, next problem number 6. Let's see. If I call x to the 4 minus 1 as u, that does not help me, because then I need to have 4x to the 3rd, x to the 3rd on the top, which I don't have it. Let us try to multiply. I think this might help. Multiply top and bottom with an x. Okay. Now I'm going to let, if this plan doesn't work, we'll think about something else. Let x square be u. 2x dx be du. X dx be 1/2 du. So I'm going to change this integral into u integral now. So this is 1/2 du on the top. X squared is u, and then that would be u squared minus 1. Perfect. This turned into a secant inverse u plus c. 1/2 secant inverse u plus c. Okay. Now we do need to replace u by whatever it was in the beginning, x squared plus c. All right, awesome. Let's see, what's the next problem we have here on the next page? We got 4 to 20 dx over x. Well, this one is not so much work, because we know integral of 1 over x is natural log of x. By the way, what is integral of natural log of x? Think about it. We will look at that problem as well soon. Going from 4 to 20. So we have natural log of 20 minus natural log of 4. Natural log of 20 over 4, which is natural log of 5. Okay. Next problem, number 8. Lot going on in here. We have a cos inverse x. We have, okay, I think what we can do here is we can plug in. So I think it would work out. Let natural log of cosine inverse x be the u. 1 over cos inverse x times derivative of that with the negative dx be du. So we can take the negative to the other side. So this whole thing would be negative du. So this turns out to be u du, but negative, which is negative u squared over 2 plus c, and which is negative u was natural log of cos inverse x squared plus c. Okay, next example. 7 to the power x dx from 5 to 3. Integral of 7 to the power x is 7 to the power x natural log of 7, going from 3 to 5 for the bounds. So 7 to the power 5th over natural log of 7 minus 7 to the 3rd power natural log of 7. I'm not going to simplify, use a calculator here to simplify. Here we have the negative exponent, so just to make it a little bit nicer, I'm going to let u be the negative x. Negative du would be dx. So this is 3 to the power u du with the negative in the front. When x is 0, u is 0. When x is 1, u is negative 1. Okay, so it turns out to be 3 to the power u over natural log of 3 going from negative 0 to negative 1. Go ahead and simplify, plug the bounds in, upper and lower bound, and I'm going to leave that for you guys to try. Next, we have t times 5t squared from 0 to 1 dt. So we're going to let t squared be u, 2t dt be du, t dt be 1/2 du. Okay, so we have this t dt. So 5 to the power u du. Let's go ahead and change the bounds. When t is 0, u is 0. When t is 1, u is 1. So here we are, 1/2. Integral of 5 to the u power is 5 to the u over natural log of 5, going the bounds from 0 to 1. 1/2 5 over natural log of 5 minus 5 to the 0 power is just 1 over natural log of 5. That is 1/2 times 4 over natural log of 5, which is 2 over natural log of 5. Okay, the next one involves a trig function. How can we handle this problem? This one involves trig. So sine 2 theta over 1 plus sine squared theta d theta. All right, let's see. So it looks like I can let let's go ahead and use identity on the top first. Sine 2 theta is 2 sine theta cosine theta. That's a double angle formula. You should remember that from trig. Now I'm going to let 1 plus sine squared theta be u, 2 sine theta cos theta d theta be du. 2 cos theta, 2 sine theta cos theta be du. Okay, so the entire numerator becomes du for me, and the denominator is u. What is the integral of du over u? It's natural log of u plus c. Just replace the u by whatever we called it in the beginning. Natural log of u. U was 1 plus sine squared theta plus c. Okay, let's see. What do we have now? Next page. D theta over 2 theta minus theta squared. So how can I evaluate this integral? There's no thetas on the top, so it looks like it's not a direct u substitution. So what I'm going to try to do is I'm going to try to complete the square here. Maybe I should do the completing the square work on the side. So if you have 2 theta minus theta square, I can write it as negative theta square plus 2 theta. And if I pull a negative out, theta square minus 2 theta, and I'm trying to complete the square, I should add half of this number squared. Half of 2 is 1. So I need to add 1 squared over here. Okay. Technically, I'm actually subtracting the 1 because if you distribute the negative, I subtracted the 1 here. To make up for it, I must add a 1 as well. So it turns out to be theta minus 1 squared plus 1, or 1 minus theta minus 1 squared. This is the completed square for me. Okay, so I'm going to replace the parentheses by what I got by completing the square. I didn't change anything. I just completed the square. And if you add and subtract 1 from an expression, you're not really changing it. So don't worry. Don't feel like you changed the expression. Okay. Here we go. We have d theta divided by... Now let's go ahead and let theta minus 1 be u, d theta be du. Okay, theta minus 1 is u and d theta be du. we can write this integral in terms of du now. So this is 1 minus u squared. Integral of 1 minus u squared is sine inverse u plus c. Remember to plug the u back in whatever you call the u in the beginning. Sine inverse theta minus 1 plus c. Okay. Next example. Looks like there's too many natural logs in here. So let me clean this really quick so I have enough space for this problem. For this one, I have too many natural logs and it doesn't look like a direct u substitution yet. What I'm going to try to do is I might pull out a y from the bottom. Leave me with 1 plus 4 natural log of square y dy. Okay, so let's see. All right, so now if I let 1 plus 4 natural log of square y as u, this bottom thing, if I let this thing as u, then I have 8 natural log of y times 1 over y dy as du. In other words, I can say natural log of y over y dy will be 1/8 du. Be 1/8 du. 1/8 du. Okay. So yeah, the remaining portion, this whole thing would be 1/8 du. All right, so I'm ready to change my integral 1/8 du over u. That's what it turns out to be. And integral of 1 over u is natural log of u plus c, the absolute value bars around. Natural log of the u was 1 plus 4 natural log of square y plus c. And that would be our solution to that integral. Okay. Let us check out the next example. Here we are, 2 root y over 2 root y dy. I think in this case, it might be helpful for me if I let root y be u. Derivative of root y, or y to the power 1/2, is you bring 1/2 in the front and you reduce the power by 1, which will become negative root y dy equal to du. Okay. So this integral turns into 2 to the power u du. 2 to the power u over natural log of u plus c. Let's go ahead and replace the u by whatever we call u in the beginning. It would be not natural log of u in the denominator, it would be natural log of 2 in the denominator. Okay. So we have 2 to the power u over natural log of 2. Now u was square root of y, and that would be our answer. Okay. Next problem, we have number 16, 6 dy over square root of y, 1 plus y. Okay. Does not look like a direct u substitution because I don't have any y's on the top and I have the extra square root of y sitting in the denominator. So what can I do with this problem? I'm going to maybe let square root of y be the u. Okay, and that would mean y is equal to u square. And when I do differentiate both sides, I would have 1 over 2 root y dy as du. Or I can say 1 over root y dy is 2 du. I can pull the 6 out. 6 is just a constant. And 1 over root d. This piece is equal to 2 du. So 2 du. On the bottom I have 1 plus u squared because y is u squared. That looks like a tangent to me. So it's 12. Tangent inverse u plus c. U, let's see, we call u as square root of y plus c. 12 tangent inverse root y plus c is what I'm left with. All right, next problem. Here we are. Okay, that does not look pretty because I don't have any x's on the top, but I'm gonna try to complete the square and see where does it take me. You cannot evaluate all the integrals. Some integrals are not integrals cannot be evaluated, so that could be the case, but you shouldn't say that until you have tried all your some indefinite integrals cannot be evaluated. So I shouldn't say that until I've tried all my resources. If I want to complete the square here, I already have plus 3. I need to add, subtract half of. Maybe I should do it on the side, completing the square work. Complete the square. So this is what I have. Remember, we add and subtract the half of this middle number squared. Half of 4 is 2. 2 squared is 4. So I need to add and subtract a 4. I already have a 3, so I'm going to add a 1 and subtract a 1 to complete this square. So I have x squared minus 4x plus 4 minus 1, which is x minus 2 squared minus 1. Good. That looks a little bit nicer now. X minus 2, square root of x minus 2 squared minus 1. All right, let's go ahead and substitute. Let x minus 2 be the u, dx is du. Okay. Are we ready to change this integral into the u form now? So we have u here, u squared minus 1 du on the top. Okay, so that looks like a perfect secant inverse u plus c. Just don't forget to call your u whatever it was in the beginning. Secant inverse u plus c. Okay, looks like that should be the end of this problem. Okay, next we have, let's see, this was number 17, and then we have number 18. All right, this one, let's go ahead and separate e to the power z times e to the power z dz. If I let e to the power z as u, then e to the power dz is du, right? So if I call this little piece as u, then this whole thing would become my du. So I'm left with e to the power u du. Integral e to the power u is just e to the power u plus c. Let's go ahead and replace the u by whatever we called in the beginning. So it's e to the power z plus c. And that's my solution to that integration problem. Okay, the next problem. Well, this one is a bit tricky. I have nothing on the top and I don't have any e to the power x on the top. Let me try multiplying and dividing top and bottom with e to the power x dx. That would give me e to the power 2x. Here, that does not help. So what I'm going to do is I'm going to go ahead and use long division. So I have 1 on the top, 1 plus e to the power x in the numerator. No. 1 is in the top, so 1 goes inside, sorry. 1 is in the numerator, so 1 divided by 1 plus e to the power x. If I multiply that by 1, I have 1 plus e to the power x, subtract 1, negative e to the power x. So this can be written as 1 minus e to the power x over 1 plus e to the power x dx. The benefit of doing this is, one, it's split into 2 fractions for me. Second, I do have the e to the x on the top, which I didn't have earlier. I'm going to split it into 2 separate integrals. The first one is just going to be 1 dx. The second one is e to the power x over 1 to the power e to the power x dx. 1 dx would be just an x. And how do I evaluate the other one? Let's see if I can do the u substitution here. So let me just call this number 1. And then I can come back to this number 1 in a second. I want to try to evaluate e to the power x over 1 plus e to the power dx. If I let 1 plus e to the power x as u, then e to the power dx would be du. Okay, so this becomes a du over u for me, which is natural log of u plus c. I'm not going to bother about c yet because I'm going to plug it back into the other expression. Natural log of 1 plus e to the power x. Okay, good. So let's call this 2. Plug 2 into 1. Integral of 1 dx is just x, and integral of the second integral we just found out is natural log of 1 plus e to the power x plus c, and that would be the end of this problem. Okay. Next we have number 20. Okay, square root of x cubed in the denominator. Let's see, so I have a square root and x cubed. So I need to think about what should I plug in as u over here. So on the top I have x, square root of x. On the top I have x to the power 1/2. When I do the derivative, I should be coming up with x to the power 1/2 when I do the derivative. So that means when I do the derivative, I should be coming up with x to the power 1/2. So I need to start with one more than this power, so that when I do the derivative, I have that numerator. So what I'm going to do is I'm going to let x to the power 3/2 as u. 3/2 x to the power 1/2 dx is du. And from there, I can say x to the power 1/2 dx is 2/3 du. Okay, so at least I have the top piece simplified. But again, if I look at this, if I go ahead and square both sides, so square both sides, I would be left with, square both sides, I would be left with 3/2 to the power 2, u to the second power 2, and 2 can cancel. So x cubed can be also written as u squared. Now I'm ready to change this integral into u integral. So 2/3 du, this is 2/3 du over 1 plus u squared. Okay, 2/3 du over 1 plus u squared. So, well, that is a nicer integral actually. Now I see a tangent inverse u plus c, which gives me 2/3 tangent inverse. Plug the u back in. U was x to the power 3/2 plus a c. Okay. And that's our answer. That's our solution to this problem. Here we are, next few on the next page. Number 21. 1 plus cube root of x to the third power. Okay, I don't have any x's on the top, so what should I do here? So I'm going to let 1 plus cube root of x as u, and then I'll try to manipulate and see. Okay, so if I do the derivative on both sides, 1 over 2 root x dx b du. Okay, and can I say root 1? Okay, hold on. We can say dx be 2 root x du. And from here, I can say root x is equal to u minus 1. Root x, it's a little bit trickier, u substitution. So we can say dx will be u minus 1 times 2 du. Yeah? So this becomes 2 times u minus 1 du, and the top is u to the third power. Pull the constant out in the front, u over u to the third minus 1 over u to the third du. So u over u to the third is actually u to the power negative 2 minus u to the power negative 3 du, which turns out to be, once we do the integral here, u to the power negative 2 will be negative 2 plus 1, which is negative 1, divided by negative 1, minus u to the power negative 3 plus 1 is negative 2, divided by negative 2, which would become a positive here. Now go ahead and replace, okay, so what, a little more simplification. So we have negative 1 over u plus 1 over 2u squared. Go ahead and replace the u by whatever u was in the beginning. We call the u as 1 plus root x. Okay, negative 1 over 1 plus root x plus 1 over 2, 1 plus root x squared, plus a c. And that's going to be our answer to this problem. Okay. Number 22, 3x plus 2 over square root of 1 minus x squared dx. Okay. Let's see. Again, it's not a very obvious u substitution, a bit tricky maybe. It might work out with the u substitution. If I call 1 minus x squared as u, let's see if it helps me. If I call 1 minus x squared as u, then I have negative 2x dx as du. But then this 2 is sitting on the top. Let's go ahead and separate these fractions. I think that might work out. So separate the fractions. This turns out to be 3x over square root of 1 minus x squared dx plus 2 over square root of 1 minus x squared dx. I'm going to call this equation 1 because I will be tackling the two integrals separately. Okay, so I'm going to be separating the two integrals. Okay, so first of all, 3x over square root of 1 minus x squared dx. This one looks like we can do a u substitution. Let 1 minus x squared be u, negative 2x dx be du, or we can say x dx be negative 1/2 du, right? So back to the integral here, I can pull the 3 out. X dx is negative 1/2 du over square root of u. And that's going to be negative 3/2 integral of u to the power negative 1/2 du, which is negative 3/2 u to the power negative 1/2 plus 1 is positive 1/2. And I'm also going to divide with positive 1/2, which is same thing as multiplying with a 2. Same thing as multiplying with a 2. The 2 and 2 can cancel, so I'm left with negative 3 u to the power 1/2. Okay, negative 3 u to the power 1/2. Now let's call the u whatever it was in the beginning, 1 minus x squared to the power 1/2. Okay, so we got the first integral done. Now let's look at the, so we just see that this integral simplifies to this. I'm not worried about the constant yet. At the end, I'm going to add the arbitrary constant. Okay, now let's go back to the other integral. That one looks like a direct tangent inverse. No, sine inverse. Sine inverse x. 2 sine inverse x. Okay, so our solution turns out to be, we just did the integral of pieces, negative 3, 1 minus x squared to the power 1/2, negative 3, 1 minus x squared to the power 1/2, plus 2 sine inverse x plus a c. Okay, that's our integral in this case. All right, next few examples, I have They are from chapter 7. Some of these were covered in Math 1A, some of these were not. So these are more natural log and exponential functions. Okay. So for the evaluate each integral. So we are in logarithm defined as an integral. So these are more all the problems involving the logs in there. So how can I evaluate this problem? So let me go ahead and try. Let u be the secant x plus tangent x. Let u be the secant x plus tangent x. And that would mean du be secant x tangent x plus secant square x dx. Okay. So if I pull out a secant x from here, then it's secant x plus tangent x dx. And this we just called, this is u. So if I take it 1 over secant x plus tangent x du will be secant x dx. And this is going to be 1 over, we can call this 1 over u du is secant x dx, right? So this integral does convert into, this is 1 over u du. Maybe I shouldn't write the du yet. So I do have 1 over u and then square root of natural log of u and du. So that entire integral can be converted into, the u integral by doing some clever substitutions. Now again, there is going to be another substitution. I'm going to let u be the t here, or y. Okay, so let natural log of u be t. 1 over u du would be equal to dt. So this integral would turn into dt over square root of t. dt over square root of t. Okay, so that turns out to be integral of t to the power negative 1/2 dt, which would be t to the power negative 1/2 plus 1 divided by negative 1/2 plus 1. And what's negative 1/2 plus 1? It's positive 1/2. So t to the power positive 1/2 divide with t to the power of 1/2, which is same thing as multiplying by 2. So it would be 2t to the power half plus c. Now, we cannot leave our answer in terms of t. We need to go back to the x that we had in the problem. So let's change it to u first. T was equal to natural log of u. So 2 natural log of u to the power of 1/2 plus c. Now again, I'm going to go back and replace the u by whatever u was in the beginning. So u was natural log of secant x plus tangent x. Natural log of secant x plus tangent x plus c. So that's our integral here. That's what our integral evaluates to or simplifies to. Okay, next, just a few more examples left, and all of these are a bit tricky. They're not direct u substitution. You have to think, sometimes you have to do another substitution in u substitution. Okay, so I tried to bring a variable t. You could bring a y or any other variable that was not used in the problem. Okay, number here, where did I go? Problem number 2. Natural log of x over x natural log of x. So let's see. Maybe I should use a slightly different color for this problem. I'm going to go ahead and use green color for this problem, just so that 2 remain separate. So in this case, I'm going to start by calling natural log of x as u. That means 1 over natural log of x times 1 over x dx will be equal to du. So now my integral turns very nice. All I have is u du because this whole thing is u, and the whole denominator with the dx turns into du. That's u squared over 2 plus c. U is natural log of x squared over 2 plus c, and that is my integral here. All right, so number 3, natural log of x dx over x square root of natural log square x plus 1. Okay. I think we can call natural log square x plus 1 as u here. Will that work? Natural log. No, let's call natural log of x as u. Let natural log of x be u, 1 over x dx be du. Okay, so we have u du, because this entire thing is du, and then square root of u squared plus 1. What should we do now? Now, derivative of the bottom is sitting on the top. That's very nice. That means I can do another u substitution. I'm not going to call it u substitution. I'm going to call it t substitution now. Let u squared plus 1 be t. 2u du would be dt. That means u du be 1/2 dt. Okay, this integral u du would be 1/2 dt over square root of t, which is 1/2 t to the power negative 1/2 dt, which is 1/2. When I do the integral, negative 1/2 plus 1 is positive 1/2. And I'm also going to divide with t, which is same thing as multiplying with the t. And now the 2 and 2 is cancelled. So all I'm left with t to the power 1/2 plus c. Now what did we call t? We called u squared plus 1 as, u squared plus 1 as t, so I'm replacing the t by u squared plus 1, and then again u was natural log of x. So final answer, natural log of x squared plus 1 plus a c is what I would be left with as my integral. Okay. All right, example number 4. Well, we've seen examples like that. So let cosine t be u. Cosine t be u. Negative sine t dt will be du. Derivative of cos t is negative sine t. So we can say sine t dt be negative du. Okay, so negative 7 to the power u du. When t is 0, cosine of 0 is 1. When t is pi over 2, from 1 to 0. So we have negative 1. Let's just go ahead and do the integration here. So we have negative 7 to the power u over natural log of 7 from 1 to 0, which turns out to be negative. I could flip the bounds, switch the bounds, and remove the negative. That might probably help make my life a little easier. 7 to the power 0 over natural log of 7 minus 7 over natural log of 7. 7 to the power 0. 7 to the power 0 is 1. So go ahead and simplify this. And that would turn out to be negative 1 minus 7 natural log of 7, which is negative 6 on the top. Negative will make it a positive 6 over natural log of 7 is our final answer. That's what we're left with. Okay. Next we have example number 5 here. 0 to square root of natural log of pi, 2x e to the power x cosine of e to the power x dx. What should I call this problem? Looks like it's got a typo. It's e to the x squared here, e to the x squared. Please correct. There is a typo in this problem. It's on page 87. Okay. So I'm going to let e to the power x squared as u. E to the power x squared times 2x dx would become du. Okay. So this whole thing is du. So I have cosine of u du. When x is 0, u would be 1. When x is square root of natural log of pi, t would be just a pi. Okay. Integral of cos u is sine u from 1 to pi, which turns out to be sine of pi minus sine of 1. Sine of pi minus sine of 1 would be sine of pi. Sine at 180 degrees is 0. At 180 degrees, sine is a y value, and sine of 1 is, see, sine of u. I'm going to leave it in this form. You can simplify with the calculator. Okay. Find the sine of 1 with the calculator. Would be pi over 2. Pi over 2. Okay. So next problem, here we have number 6, dx over x, natural log of 10 over x. First of all, I'm going to write natural log of 10 over x in terms, log to the base 10 of x in terms of natural log of x. If you remember from college algebra or intermediate algebra, you can write log to any base in terms of natural log. So this will be natural log of x over natural log of 10. This becomes dx over x, and then natural log of x over natural log of 10. Natural log of 10 goes on the top. Natural log of 10 dx. Now natural log of 10 is a constant. I'm going to pull it out. Now it looks like a nicer problem. Let natural log of x as u. Let natural log of x as u, 1 over x dx be du. The natural log of 10 is a constant. We don't need to bother about that. It can be sitting in the front. Natural log of 10, 1 over u du. Natural log of u plus c. Okay, let's replace the u by whatever we call the u if it's natural log of x plus c. So here's our solution, and that's the end of this video. As we talked about lots and lots of integration techniques, practice a lot of integration techniques, and memorize all the formulas in the beginning of the section, all the derivatives and integration rules.